तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us look at the quiz paper and then we start with question 1. This is a set of true or false questions. I will read out the question and then give you the answer. Since, in case of doubt, please raise the question and then we will clarify this. The first part said the phase trajectories of a non-autonomous dynamical system can intersect themselves or each other. We know for sure that for an autonomous system they can't do so. For a non-autonomous system there is no such constraint at all, because the rules of the game change with time, and therefore if things intersect themselves after some time it is a different rule and a different trajectory. So a possibility of this kind exists. So a phase trajectory can come along, go through here, and although at this point you might ask, isn't the future determined uniquely in terms of the present, the fact is you are reaching this point at two different times and the rules of evolution are different in the two cases. In one case it would have been this, in the other case it would have been that. So it is quite clear that they can intersect themselves if it is non-autonomous, and that is a true statement. The Euler-Lagrange equations of a system do not change if an arbitrary function f of q1 to qn and t of the coordinates and time is added to the Lagrangian. This statement is not true. If the total time derivative of such a function is added, then of course the statement is true. But an arbitrary function cannot be written as the total time derivative of another function, and therefore this is not true completely. There are functions which do not have primitives, which cannot be integrated, there is no definite integral. Square root of sin x, there is no function of which square root of sin x is the derivative. So in general you can't write an arbitrary function as the total time derivative of another function, and therefore this statement is not true. So please read all the clauses in the question, all the statements completely. Liouville's theorem says that a volume element in the phase space of a Hamiltonian system does not change under time evolution, and the statement asked is, this is true only for time independent Hamiltonians and is not true for time dependent Hamiltonians, and the statement is false, because Hamiltonian flow we saw is volume preserving regardless of whether there is explicit time dependence in the Hamiltonian or not. It is another matter that the Hamiltonian is not a constant of the motion if it is explicitly time dependent. That is certainly true, because dH over dt is equal to delta H over delta t, and that is not 0. So that is certainly not so, but the fact that the measure is preserved in phase space, the volume element is preserved, that is certainly true even if you have time dependence. So the statement is false. Noether's theorem applies to both continuous symmetry transformations, for example rotations, and discrete symmetry transformations, for example reflections, and it is a false statement. We can't define a Noether current. Remember the way we derived a conserved quantity from Noether's theorem, which was to ask what happens if you make an infinitesimal transformation, and if a transformation is discrete there is no infinitesimal version of it possible. If you have a reflection in a mirror, either you have a reflection or you do not. I mean, if you reflect twice you get back to where you were, it is like parity. So there is no infinitesimal transformation, and therefore the theorem does not apply as it stands. It is a false statement. The next one was a damped nonlinear oscillator has the equation of motion x double dot plus alpha x dot minus beta x plus gamma x cubed equal to 0. This is a very famous model of a nonlinear oscillator. It is called the Duffing oscillator. Let me write that down, since and there is a little bit of history attached to it. It is a prototypical model of a system which has a nonlinearity as well as dissipation. The dissipation comes because you have a friction term here with a positive coefficient, and if you did not have this nonlinearity, this would look like an inverted oscillator, because you see you could write x dot equal to V, and then V dot, that is this term, is equal to minus alpha V, so that is a friction term as you can see straight away, plus beta x minus gamma x cubed. This portion quite evidently comes from a potential, the derivative of some potential with respect to x. But you see, if it were a simple harmonic oscillator, you would not have this nonlinear term. You would have a linear term and it would appear with a minus sign, because the restoring force should take you towards the center of oscillation, and this would correspond to a plus half kx squared potential, but in, or beta x squared potential. Here you have got a plus sign for the beta. So what does the potential look like? We know that V prime of x equal to minus beta x plus gamma x cubed, because that is what the force is, V prime minus V prime of x. So therefore V prime of x is minus this guy here. This is what the force was, the f of x is minus V prime of x, and that is given by this. So what is V of x? Apart from a constant, V of x equal to minus beta x squared by 2 plus gamma x4 over 4. And what does that potential look like? If I plot as a function of x, I plot V of x near the origin, since alpha, beta, gamma are all positive constants, you have been given that as part of the information. This is an inverted bowl, and that bowl takes you up, this beta gamma x4 takes you up. So it is clear that this potential looks like this fashion. So it is a potential with an unstable critical point at the origin, V equal to 0, x equal to 0, that is a critical point, and that is of course an unstable critical point, because you have a maximum of the potential, but you have two minima, one at this point and one at this point, which are given by taking this quantity and equating it to 0, where the force vanishes. So you have roots at x equal to plus or minus square root of beta over gamma, and those are these 2 points, and they correspond to minima of the potential, and therefore these would correspond to stable oscillations. If you did not have dissipation, if you did not have this term, then of course there would be stable oscillations. The moment you have this term, it is clear that things are going to fall into it, depending on whether it is underdamped or overdamped, things are going to fall into it asymptotically. So there will be two stable asymptotically stable critical points at plus square root of beta over gamma and minus square root of beta over gamma, these 2 points, they would be stable, and this guy is unstable in the middle. So this oscillator, this is a very famous example of nonlinearity, as I mentioned. The more general problem is when you take this oscillator, not 0 on the right hand side, but you apply a sinusoidal force to it. So you have a forced damped nonlinear oscillator, and the forcing would be perhaps go like A cos omega t, where A is the amplitude of the external force and omega is the frequency of the external force. This is a non-autonomous system, because you are putting in energy into the system or removing it, you are actually putting a time dependent force on the system. So this is non-autonomous, this dynamical system is non-autonomous once you put a t here, and it is an exceedingly complicated system to analyze, unbelievably so. In fact, the full analysis is not complete, it probably will never will be. The reason is you have a parameter space in which you have 1 parameter alpha, 2 beta, 3 gamma, the amplitude of forcing 4, and the frequency of forcing 5. Now a 5-dimensional space of parameters is a very rich one, all kinds of things can happen. You could get rid of one of them, you could say that is a time scale, I fix a time scale such that alpha is equal to 1 or beta is equal to 1, you still have 4 of them left, and that is a very complicated mess. This system is a 2-dimensional phase space, 1 degree of freedom, but once you put forcing in it, it becomes non-autonomous, and then you have to look at it in extended phase space x, v and t, and this system could display chaos. Even a simple thing like this can display chaos. and in fact it does for certain parameter values, it adequately large values, it displays chaotic behavior, it displays all kinds of other behavior. One interesting question is, suppose I do not have this 0, is it possible to have a periodic trajectory even though you have dissipation, even though you have this thing here, is it possible to have some initial condition for which the system becomes periodic, that is it damps out but then it has enough energy to cross here, goes over to that side, and then its energy is given to the system once in a while, as you can see, and then does it become periodic? Is there an isolated periodic trajectory in this? And the answer in this case is no. There is a rigorous theorem, you can show this, I will do that a little later, to show that this system cannot have an isolated periodic orbit, and indeed everything would fall into this point or that point. So all points in the phase space, if I plot x versus little v, the phase space, there is an unstable critical point here, there is an asymptotically stable critical point here, and an asymptotically stable critical point here. Then the interesting question you can ask is, if I start somewhere here, every point is on some phase trajectory, if this is my initial condition, would it fall into this or would it fall into that? And that is not easy to answer. It turns out once again that depending on the initial conditions you could fall into this or that, and all points which fall into the left attractor are called points belonging to the basin of attraction of this critical point, and or the basin of attraction of that critical point. And these basins of attraction are very intricate in structure. In general, for arbitrary nonlinearities, they would have very riddled fractal structure. So the whole of phase space would be incredibly mixed up in a crazy fashion. Some parts would fall into the basin of attraction of this, a small neighboring initial condition could make you fall into this, and so on. Think of it physically, I start off, it starts oscillating in this, and then the friction occurs, and now it is possible that the system comes here and then does not have enough energy to cross that, and then it will eventually fall into this. But if it had an infinitesimally greater energy, it would fall into that, does not have enough energy to come back here due to the damping, it falls into that. So you can see immediately that small changes in initial conditions could make you go to this attractor or that attractor. It is for these reasons that this model is very popular. There are books written on this single model, on the Duffing oscillator. Okay. The next question was, the Laplace-Runge lens vector is a constant of the motion in the case of the sorry. The linear matrix, yeah, sure. I mean, if you do that in the original case, there is no center manifold, there is no eigenvalue with real part equal to 0. So the analysis will give you reasonably correct results, will give you correct results sufficiently close to one of the critical points. So this is a linearizable problem, yes, definitely. And if you did that, you would discover this point is unstable and these points are stable, critical points. Yeah. Okay. The Laplace-Runge lens vector is a constant of the motion in the case of the potential minus k over r, in other words an attractive 1 over r potential, but not in the case of a repulsive 1 over r potential. This is not true, because this lens vector has nothing to do with whether k is positive or negative, the constant of the motion in both cases. It is just that when k is negative, the orbits are all ellipses, they are all bound orbits. On the other hand, the bounded orbits, if k is positive, then you have a repulsive potential, and then the orbits are all hyperbolas, but all the orbits are guaranteed to be conic sections in this potential anyway. But this has nothing to do with whether the Laplace-Runge lens vector exists or not. That is the symmetry of the problem, and has nothing to do with whether k is positive or not. Okay. And we derived the relation dA over dt equal to 0, and I never made use of the fact that k was either positive or negative. So that is okay. A Legendre transformation from the Lagrangian to the Hamiltonian can be made only if the Hessian matrix d to L del. So the statement is, the transformation from L to H can only be made if d to L over delta qi dot delta qj dot is singular. This matrix is singular. That is not true. You can make this transformation only if the matrix is non-singular. That is the whole point. But I have said singular there, and if you had your eyes open, you would have seen that it says singular, and therefore the statement is false. But the next statement, where the Hamiltonian goes into the Lagrangian, so the question is, can you go from the Hamiltonian to the Lagrangian? The condition required is that this matrix is non-singular. So if this is singular, this is not possible. If this is non-singular, this is possible. So in all cases the second statement is true. This is only to find out if at 8 a.m. you are awake or not. Yeah.
In the Duffing oscillator.
Yeah.
We did make a distinction between asymptotically spiral point,
Yeah.
stable point, and asymptotically stable point. Won't it be a spiral here?
Yeah, in general it will be asymptotically stable. So the statement asked was the system has two asymptotically stable critical points, and that is true. They are asymptotically stable, they are not stable.
Yeah, but
yeah.
During your eigenvalue analysis, we clearly stated there is a definition for asymptotically stable and
yes.
asymptotically spiral.
No, no, that is not true. No, if the real part of the eigenvalue is negative, then it is asymptotic stability. If the real part is 0, then it is a center, as you can see. If the real part is positive, it is unstable, that is it. Okay. Whether it is a stable, asymptotically stable node or an asymptotically spiral point, stable spiral point, that depends on the details of the parameters, but that is not, both of them are true when the real parts of the eigenvalues are all negative, that is all that you need. So whether it is a spiral point or whether it is going to be a node would depend on how heavy the damping is. If I start off something here, if the damping is very high, it could just trickle down here and stop. On the other hand, if the damping is not sufficiently high, then it could go here, it could oscillate here and come back here with a smaller amplitude and then go back and keep doing this about this point and stop here. That would be a spiral point, and that would depend on the size of the damping relative to the other coefficients. But in all cases asymptotic stability for those 2 points. Okay. Now the next one, I was surprised at the answers, because a ball bounces up and down on the horizontal on a horizontal floor under the influence of gravity. The statement is, if the collisions with the floor are assumed to be perfectly elastic and air resistance is neglected, the time period of the motion is independent of its amplitude. That is not true. We know that if I take this object and drop it, the time it takes to hit the ground is going to depend on the height, of course, and if it is a ball, it is going to bounce up and down. So this is, there were people who take the true, and I was wondering why, because the effect of the JE has worn off or what. Okay. The Hamiltonian of a charged particle moving in a time dependent electromagnetic field is gauge invariant. We know the Hamiltonian, we know it is H is equal to P minus EA whole squared over 2m plus E phi. It has got explicit dependence on the scalar and vector potentials, so it obviously can't be gauge invariant. It has got explicit dependence there, so it is not gauge invariant, not true. The question is, how does it change if you make a gauge transformation, and that is what was asked in the fill in the blanks at the end. Okay. What I found interesting was that people have said yes, it is gauge invariant here, and then have calculated non-zero changes. This is what yes. Whenever I see that kind of contradiction, I am reminded of this guy who was asked how many chapatis you could eat on an empty stomach, and he said 19. So the guy who told him the joke said, you are an idiot, because after the first one, you eaten the first one, your stomach is not empty anymore. So he goes home and calls his wife and asks, how many chapatis can you eat on an empty stomach? And she says 4, and he says, oh God, if you had said 19, I would have told you a good joke. So this is sort of mutually contradictory things. Okay, all right. The fill in the blanks, the first question was the Lagrangian, was a simple pendulum Lagrangian, and you are asked for the energy of the separatrix. That is twice mgl, and I think most people have it right, because with the zeros that we have got, the potential goes like this, etc., and the separatrix corresponds to this energy. So you basically have mgl times 1 minus cos theta, and this is twice mgl for theta equal to pi. So that is the maximum of the potential, and whatever is the energy there, that is the answer. It is twice mgl. Okay. Now the next question, yeah.
Sir, in this simple pendulum question,
yeah.
sir, can we take it as a bob and a spring?
by definition for me, then there is no question of any other kind of motion at all, right. It would start bending, it would start flipping and so on. So from the beginning for me a simple pendulum is a frictionless device in which you have a light massless rod and a heavy bob, and it is a rigid rod, so that both rotations and vibrations are possible, otherwise it is complicated. Even if it is a bob with a string, the string should be inextensible, otherwise you run into trouble, right. So then it is a very complicated problem. Since you raised it, let me point out that one of the very complicated problems, the reason we introduced the action was also because of this kind of problem. If you took a simple pendulum of the kind he is describing, namely a heavy bob attached to a massless string, and let us say the string is not extensible, it is a fixed length. Now you start oscillating it, and as you oscillate it, suppose you slowly shorten the string. So imagine, for example, you made a hole in the table and you put the pendulum through it and it is oscillating there, and then you gradually draw the string out so that the length of the string becomes less and less. Then of course the motion of the pendulum is going to look like this. It is going to start here and then it is going to go here, it is going to keep doing this, it is going to go backward. Now then the question is, what happens to the frequency, because the length is changing and you know the time period is 2 pi square root of L over G, and L is very slowly being decreased. Therefore you know that the time period is going to decrease slowly, but the question is, can you solve this problem? And this is one of the very important problems in mechanics. Yes, you can, using the fact that the action of the system is actually an adiabatic invariant. In other words, the action does not change essentially. So this is one of the reasons for introducing the action in classical mechanics, that they can be used as adiabatic invariants. When you perturb the system sufficiently slowly, it turns out that the quantities that remain constant are the action variables, and that is one of the reasons. And there are many papers on this, including a famous paper by Chandrasekhar himself on this pendulum being decreased, and by Littlewood and other famous people. Okay. But the pendulum we have in mind is a much simpler device. The next question gave you a Lagrangian, and not surprisingly most of you discovered that this equation of motion was in fact that of a damped simple harmonic oscillator. So you see, you have got dissipation in this problem and I can still describe it by a Lagrangian. So the lesson is supposed to be that dissipative systems could, under suitable conditions, still be described by Lagrangians, and it takes us into some fairly non-trivial things, because we have L is a function of q dot and t, and that is e to the gamma t times the harmonic oscillator m q dot squared minus 1/2 m omega squared q squared. This portion alone is a Lagrangian for the simple harmonic oscillator, the undamped ordinary simple harmonic oscillator. But I have an explicit time dependent factor here, and if you compute the equation of motion, you discover that q double dot plus gamma q dot plus omega squared q equal to 0. Actually it gets, this whole thing gets multiplied by m e to the gamma t, and it is not clear to me why you do not score off these things, because neither m nor e to the gamma t is 0. So you really get this, and the fact that you leave it at that point with m e to the gamma t and not bring the equation, all the terms to the left hand side and so on, to me is a symptom of laziness, which perhaps is a reflection of the semester that you people are all in. So, but you won't do that in the JEE, for the simple reason that you are worried about some short-sighted or myopic examiner giving you 0 where you should have actually got 1, in which case your entire world line and future history would have got changed. So you worry. I always have found this very puzzling, how it is that human beings get adapted to things, and of course by the time you come into your 4th year there are so many exams you have gone through that exams do not hold any terror for you. I have had an experience where the student comes to an exam without a pen and he borrows my pen. The reason is he has his toothbrush there instead of his pen by mistake. Of course when he took the joint entrance exam, I have no doubt at all that his parents stood on either side of the exam hall and watched with binoculars to see whether he had written the roll number down correctly, not to mention the fact that he had 4 water bottles and 6 spare pens. But after 4 years things become. So this is the equation of motion of a damped harmonic oscillator. So important lesson, damped dissipative systems sometimes can be written in terms of Lagrangians. Yeah.
Sir, is this Lagrangian true for any other damped system?
There is a general prescription by which you can write down not a potential energy. You know that for conservative systems of the kind we have in mind, the Lagrangian can be written as T minus V very often, and they lead to Newton's equations. But this V could be replaced by something called U, which is called the Rayleigh function, which for certain kinds of dissipation would play the role of a potential, and therefore you can write the Lagrangian equations down once again. So the answer is in general no, but in special cases yes, you can do so. What's interesting is we know the phase trajectories in this system, they are all going to go and fall into the origin, and that is very clear. So is this a measure preserving flow in Q and Q dot? Is this measure preserving? Because wherever I start, all these fellows are going to fall into this point here. So it is clear the entire phase space is going to shrink to a point. No matter where you start, it is going to shrink to a point. So is volume preserved in phase space? No. In this phase space, no. But now you can ask, can I go to a Hamiltonian? Can I take this system and go to a Hamiltonian? So let us close our eyes and do that. Let us see what happens to the Hamiltonian here. We know at the back of our minds that this is a dissipative system, and therefore any Hamiltonian would be explicitly time dependent if it existed. So let us see whether we can do that. We have to define P is delta L over delta Q dot, and that turns out to be mq dot e to the gamma t. So please notice P is explicitly got time dependence in this form, formally at least. So if I solve for Q dot equal to P over m e to the minus gamma t. So what happens to the Hamiltonian? H is a function of Q, P and T, and that is equal to PQ dot, so that is P squared over m e to the minus gamma t minus the Lagrangian, which is e to the gamma t, times 1/2 m Q dot squared, but Q dot is this guy here, so it is P squared over m squared e to the minus 2 gamma t minus 1/2 m omega squared Q squared. So this works out to P squared over 2m e to the minus gamma t, this gives you minus gamma t, plus 1/2 m omega squared Q squared e to the plus gamma t. It has got explicit t dependence. So in the PQ phase space, is measure preserved? It is a time dependent Hamiltonian. Are area elements preserved in the PQ phase space? Yeah, they are. Look at our first part C of the first question. It said Liouville's theorem says that the volume element in the phase space of a Hamiltonian system does not change in magnitude under time evolution. This is also true for time dependent Hamiltonians. So it is true here too. So you see, this begins to tell you, even the simple example, that the change from Q dot, Q and Q dot to Q and P could be quite non-trivial. One of the great advantages of changing to the Hamiltonian framework is that the flow becomes measure preserving, even if there is time dependence in the Hamiltonian. In a sort of crude sense, you can see, in a very crude way, you can see what is happening, because you see volume elements in the QP phase space, a little volume element would not change as time goes along. It is a non-autonomous Hamiltonian, so you must really look at the extended phase space with T also sticking out. But in a very crude sense, we know that for a damped harmonic oscillator, if I solve these equations, Q goes like e to the minus gamma t over 2. It has got a damping factor, and Q dot also goes like e to the minus gamma t over 2. So in this phase space, look at what happens to P. This goes like e to the minus gamma t over 2, this goes like e to the plus gamma t, so P goes like e to the plus gamma t over 2, Q goes like e to the minus gamma t over 2, and therefore dP dQ does not change. So this is an interesting problem where you see that the fact that it is time dependent explicitly does not change the general statements about the preserving of the measure, and the fact that you have a very complicated kind of shrinking of volume in the QQ dot phase space can be overcome by changing to a new variable. And this is one of the great advantages of the Hamiltonian framework, and this is a simple instance where you can explicitly see this happening. Okay. Yeah.
Conservative dynamical system as the one in which volume element is preserved.
Yes. So a Hamiltonian system. Now the question is, can you call this conservative? See, the fact is those things were useful when you didn't have, when you had only autonomous systems. The moment you have non-autonomous system, then this distinction becomes completely meaningless. Okay. All right. Then where were we? The third question was the orbital angular momentum. I was a little surprised by the answers here, but let me write this down. The number of people came close to the answer, but they ended up writing the kinetic energy rather than the angular momentum. So you see, the kinetic energy of a free particle is 1/2 m. In Cartesian coordinates it is x dot squared plus y dot squared plus z dot squared. If you wrote this in angular variables, spherical polar coordinates, then of course it is equal to 1/2 m r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. This is certainly true, but if you wrote this in the Hamiltonian framework, then this is equal to p squared over 2m, where p is the momentum vector dotted with itself. And of course you could write it as px squared plus py squared plus pz squared over 2m, but if you wrote this in spherical polar coordinates, then this is equal to the radial momentum squared over 2m plus the angular momentum squared divided by twice the moment of inertia, and this is 2m r squared. Now what is L squared? L squared, if you work this out, all you have to do is to take r cross p and square it, then this turns out to be equal to p theta squared plus p phi squared over sine squared theta. And that is it. There is no 1 over 2m r squared. That came only when you wrote it as part of the kinetic energy, otherwise it is dimensionally wrong. So whenever you write these answers, check the dimensions, and that way you won't have answers where the first term has one physical set of physical dimensions and the second term has another set of physical dimensions. This is not possible. Now what are the physical dimensions of these guys? What are the physical dimensions of p theta? Angular momentum, and p phi angular momentum. Theta does not have dimensions at all. Each of these guys has dimensions of angular momentum. What are the physical dimensions of PR? Yeah, it is clearly not the physical dimensions of angular momentum, it is a radial momentum. So it has the dimensions of energy multiplied by mass, square root of. So this has got different physical dimensionality. It is obvious because R and PR, the Poisson bracket is 1, and the Poisson bracket of theta with p theta is equal to 1, and so on. So it is immediately clear that the physical dimensions of PR would be different from those of p theta. The radial momentum would have a different physical dimension because there is a length sitting there in R. Okay. All right. Then the question about Poisson brackets, that was straightforward and most people have the answer. Just a piece of algebra. So we know that r squared r dot p is equal to 2 is twice r squared. The next one was the Hamiltonian. You are given x dot is y dot is mu x minus x squared. All you have to do is to integrate this, and everyone has got this answer right. So x dot equal to y dot equal to mu x minus x cubed. There are people who write mu like u. Please don't do that because u looks like a velocity to me. So h of x comma y is in fact equal to y squared over 2 minus mu x squared over 2 plus x cubed over 3 plus in general some arbitrary constant which is irrelevant completely in general. Okay. Then the nonlinear oscillator, the sextic oscillator, the thing that goes like potential goes like k x to the power 6 and the time period is proportional to the amplitude to the power minus 2. So you have a Hamiltonian which is p squared over 2m plus k x to the power 6 and you are asked for the time period. Well, the phase trajectories in the x dot space for example would be some kind of ovals of this kind, not ellipses, where x dot squared plus x power 6 is equal to some positive constant and you are asked to find what the time period is, and the t goes like integral 0 to a 4 times this dx over x dot, and x dot would look like E minus the potential, but the E is proportional to a to the 6, so a to the 6 minus x to the 6. So apart from some constants, this is what the time period is, and all you have to do is to put x equal to au, make a change of variables, you get an a up there and you get an a cubed here, and this becomes 1, and therefore this whole thing goes like 1 over a squared integral 0 to 1 du square root of 1 minus u to the 6. And like I explained on an earlier occasion, this integral exists, it is just a square root singularity at u equal to 1, some finite number, and then it is 1 over a squared. So it is a to the minus 2. Since I said t is proportional to a to the r is minus 2 not plus 2. Some people have lost a mark because they wrote plus 2 and I am sure that they knew what was going on, it is just that they did not read it carefully. Okay. Then this is the bead moving on a hyperbola. We worked out the case of the problem, the case of the of the circle. So there are some people who wrote down the answer for the circle. That reminded me of this, how many chapatis can you eat? I mean, it's forever it shall be a circle. So this hyperbola looks like this here, and this is z, this is y, and you are given z equal to square root of a squared plus y squared minus a squared minus a. Now that is the upper branch of this hyperbola. There is another one here intersecting at 2a here, and then of course you have to write down what the kinetic energy is, and if you wrote the kinetic energy down, it is z dot equal to, this becomes a rho squared once you start it rotating, it becomes rho dot divided by a squared plus rho squared, square root of this guy, that is what z dot is, and then you have to compute 1/2 m rho dot squared plus rho squared omega squared plus z dot squared, which is rho squared rho dot squared over a squared plus rho squared, and you have to remember to remove the square root because you are squaring this guy, and then p equal to delta L over delta rho dot, so it becomes equal to m rho dot times 1 plus rho squared over a squared plus rho squared. The fact that you have not written it as a squared plus 2 rho squared over a squared plus rho squared has been condoned, but this is the answer. There is no square root or anything like that. Okay. That is the momentum conjugate to the radial variable rho, the actual distance rho. Okay. Right. The next one was an old problem, the precession of a particle of a magnetic moment in a constant magnetic field, and I assumed that this problem is well known to you. So you have a magnetic field in this direction, and then you have the xy plane, and you are told d mu over dt equal to g times mu cross b. And you see you can resolve mu into the z component along the field and two transverse components. Take dot products on both sides with respect to b. So take b dot whatever it is, then you can see d over dt of mu dot b equal to 0. B is a constant field, does not change, you take dot product, take it in, then this is 0. So it says the component of mu along the direction of the magnetic field does not change. The other two components would precess around, and as you know uniform circular motion in the xy plane is equivalent to two simple harmonic motions at right angles. So you know the answer, mu x is going to obey a simple harmonic oscillator equation. So it is clear that you are going to have d mu x d2 mu x over dt2 equal to minus gb whole square mu x, and similarly for mu y it obeys exactly the same equation except the initial conditions are different. Now I would not accept your writing d mu x over dt or d2 mu x over dt with the d mu y over dt on the right hand side, because then you have to tell me what is the equation for d mu y over dt. So that is not complete an answer, you have to say what is the equation for mu x. So it can only involve mu x, I should be able to solve for this thing. So writing it in terms of another unknown does not give me the equation for it, and that is not acceptable. Okay. Incidentally you could also ask what is mu dot this equation on both sides, that too is 0. So it is clear that d over dt mu dot mu equal to 0. In other words the magnitude of mu is preserved. So the component of mu along this field is preserved and the magnitude is preserved, therefore the only thing it can do is to move on the tip of a cone, it can precess in the tip of a cone. Of course you could ask, can't it do this and come back, why does it have to make a circle, and that is what this equation proves. It does not do that, it makes full circles, goes around and does some. So the tip of this traces a circle, or the x and y components do simple harmonic oscillations. So the famous problem of precession in a magnetic field. The next one surprised me because it just said the simple potential has a simple minimum at some point x naught, and one asked for the frequency at this point, and that is harmonic oscillations. So the frequency is extremely straightforward to write down. So as a function of x, v of x has some minimum somewhere at some point x naught, a simple minimum, and you are asked what is the frequency of small oscillations about that point here. So all you have to do is to write the energy down as 1/2 m x dot squared or velocity squared plus the potential energy and do a Taylor expansion at this point. So the first term is v of x naught at some constant plus x minus x naught v prime of x naught, but that is 0. The whole point of this being a minimum is that v prime of x naught is 0. So there are lots of people who got answers with v prime of x naught or v prime of x. Of course the frequency is a constant, it can't depend on where you are in this problem. We are asking for small oscillations about the point x naught, so whatever derivative occurs must be at the point x naught, right, plus the next term. So this thing is written in this form, plus x minus x naught whole squared over 2 v double prime at x naught. So this is of the harmonic oscillator form, except you have shifted the center of oscillation to x naught instead of 0, but that does not change the frequency, and the frequency omega equal to the square root of the spring constant divided by the mass. The spring constant, the role is played by v double prime x naught, so it is just v double prime of x naught, and you must not forget the mass for dimensionality. So that is the answer. Okay. And last of all, the Lagrangian of a charged particle in an electromagnetic field is given to you, and then you make a gauge transformation and you ask what does the Hamiltonian do, and we know that the Hamiltonian will change because in general remember a gauge transformation on the electromagnetic fields is like a canonical transformation on the Hamiltonian, and we know that the Hamiltonian under a time dependent canonical transformation is not the old Hamiltonian written in the new variables, but there is also an extra partial derivative term which is the partial derivative of the so called generating function of the canonical transformation, and that is what will emerge here. So you start by saying L is equal to 1/2 mv squared plus E A dot V minus E phi, where these are functions of r and t. Therefore the momentum P is delta L over delta V equal to mv plus EA, we know that, and then the Hamiltonian, which is a function of r, p and t, turns out to be P minus EA whole squared over 2m plus E phi. And now I come along and say, ha, I don't like this, I make a gauge transformation. So I write L prime equal to 1/2 mv squared plus E A dot V plus E grad F dot V minus E phi plus E delta phi delta F over delta T. So I change A to A prime, which is A plus grad F, and phi to phi prime, which is phi minus delta F over delta T, and this is what the L prime is. Therefore the P prime in this case is delta L prime over delta V, and that is equal to mv plus EA plus E grad F. You got an extra piece here, you have to put that in, and then the new Hamiltonian of R P prime and T is equal to P prime dot V, where you must eliminate for V and write in terms of these other quantities, minus L prime, P prime dot V minus L prime. So this term just floats around, it gets cancelled on both sides once you do this, and then this thing reduces to, and then you discover this becomes equal to H of R, P and T, which was the original thing here, minus delta F. Very important to remember, this is a partial derivative, otherwise not true. If you made a gauge transformation that does not explicitly depend on time, then it is equivalent to a canonical transformation which does not depend on time, and therefore the Hamiltonian would be just in the new Hamiltonian would be just the old Hamiltonian function in the new variables, where you substitute it in terms of the new variables. Otherwise there is an extra partial derivative term, and that is this term. So this is not the total derivative. The Lagrangian changes by a total derivative. L prime differs from L by df over dt, d over dt of EF, but the Hamiltonian differs by minus E delta F over delta T. It is very different, these are very different quantities. So that was, some people did get it, but not too many. Okay. Let me quickly go over the problem set 3 in case you have it. Yeah, sorry. Pardon me. Okay, we are out of time, that means, okay, so we should stop here and let us do this. I would like to spend some more time, so perhaps tomorrow morning we will go over problem set 3, and we could do the following if it is okay with you, otherwise we go on to something else, and that is either we look at all the earlier problem sheets tomorrow or I start a new topic, it depends on you.